All right, guys, welcome to this course, Introduction to Data Science. This is a 5-evening course. It will start from Monday to Friday, that is from today all the way till end of Friday. We will be having sessions from 7 p.m. to 10 p.m. Pacific Standard Time. This will be sort of an interactive course. We'll talk a lot. We'll also walk through some labs. We'll go over the core ideas of machine learning. Machine learning is a vast subject. It is so vast a part of computer science that now it's being carved out as a separate department in most universities. And as completely different programs that undergraduates also can be a part of. So this subject, of course, it is to a limited depth that we can go in 5 days, but I'll try my best to give you a strong feeling for this subject and what it is. So we will talk about the core ideas. What are we going to cover? First, we'll cover what is data science. Perhaps the biggest part of data science, what are its components? We'll talk about it. One of the biggest components will be machine learning. Machine learning has taken on dominant importance in contemporary society. It variously goes with the name of AI more loosely. There are core algorithms of machine learning that we'll cover. We'll cover regression, we'll cover classification, we'll cover clustering, we'll cover dimensionality reduction. Now, what these words mean, if it doesn't mean anything to you, do not worry. That's what this course is about. We'll learn about those things. And so we'll learn about those things. And along the way, we'll also learn why they matter. The one topic that we will not cover, but is of quite significance, is reinforcement learning. Right? I'll touch upon it if time permits, and we'll go from there. Now, today will be a little bit light. I'll give you the big ideas. We won't do that many labs. I'll walk you through some code. Nevertheless, there wouldn't be things for you to do. And today, my team will post some code onto the course portal. Download it, play with it, have fun with it. But tomorrow when we come, we'll go and do a little bit more intensive labs. I'll walk you guys through those labs, and again, you will have little exercises, perhaps little quizzes that you can play with. It is all for your self-evaluation. Absolutely nobody is going to look at how you did on your quiz, right? It is completely private, and you can take the quiz as many times as you want. Many people tell me that it's good interview preparation, right? So you can have fun with that. So that's the format. So today we'll start now with machine learning itself, or data science. People, when they talk about data science, what do they mean by data science? What is data? Data is the plural of data. And when you say that we are going to do or talk about the science of data, there is something paradoxical about it. Science itself is about measurable things. There is a famous quote by Lord Kelvin, a physicist, who said that a thing is not science, a subject is not science, until it talks in terms of empirical, measurable quantities. Measurements yield data, and therefore data science can be, and is, its scope is all of science. And yet when we say the word data science, people today more loosely mean specific things. It's about becoming skilled at manipulating data, at visualizing data, and at building prediction models with data, and recognizing patterns in data. I'll repeat that. The skills that people expect in a data scientist are ability to do data wrangling, right? Why do we do data wrangling? Because data comes to us in all sorts of bizarre forms. It never comes in the form that you want it. It will have missing values, it will have errors, right? And somebody will give you the data, you want a CSV, they'll give it to you in a PDF, right? Or they'll give it to you in a completely different column names and et cetera, right? Or it will be in Excel, things like that. Data comes in different formats, but more than that, even if you could make it tabular, those of you who have been doing databases know that It is often a core. The whole process used to be called extraction, transformation, and loading. And these days, in view of the scaled out data, big data, we call it extraction, load, and transform. What is the journey of data wrangling? You set out what you want the data to look. It must look a particular way. And in the context of data science, in terms of machine learning, there is a particular format that is often called the tidy data, based on the classic work that goes a few years ago. I won't go into the whole data wrangling subject, but if you put your data in such a way that each row is one observation, it is about observation about something, right? One entity or one unit of observation. It may be multiple things. So example would be today here in Fremont, at this moment, what is the temperature? What is the pressure, right? What is the humidity? What's the wind speed? All of it put together, these attributes collectively specify what the weather is here at this moment, wouldn't it? Right? And you can add a few more attributes. But let us say that you did have that, you would consider it to be one unit of data, right? Or one datum. And then that datum has features, temperature, atmospheric pressure, wind speed, humidity, and so on and so forth. Likewise, another location would have another such set of values. When you make each location's value at a given point in time as one row, you are following what we call tidy data. For machine learning purposes, that is the beginning point. But for majority of your work that you will do in this field, you will realize that to even reach the starting point, you have to work very, very hard. In fact, data engineers, that's what they do. They work with data at massive scales sometimes, data that comes from heterogeneous sources, and they rationalize the data and bring it into the format that you want. That journey is the journey of data wrangling. Once you have the data, so that is one piece of the puzzle. And give me a moment, and I would like to write these things out. So we said that there are four pillars. Data wrangling is one, data analysis is another. It's a significant pillar, right? Data visualization, part of it is visualization, and we'll have something to say about data visualization shortly. I'll just say data modeling. Modeling comes after that, and that is making machine learning models and whatnot. The machine learning comes after that, but before that comes data wrangling that we talked about. You saw the necessity of data wrangling. In your life, you must have seen the data never comes the way you want it. And enough said about it. If you ask, what does a machine learning engineer do in the workplace? What does a data scientist or variously called AI researcher do? The outward perception would be that, oh, they keep thinking. Maybe they look at the sky and think for half a day and then write down a loss function, a mathematical loss function, or come up with a better neural architecture or have some idea or something like that. That would be the perception you would like to have. Do something very deep, mathematical, clever. Reality is, even the best of the machine learning experts spend 70 to 80% of the time doing this, data wrangling and data analysis and visualization. Data wrangling is a necessary evil. You can't get away with it. Data analysis and visualization is a different cup of tea. So let me talk about it. Once you have data in the right form, before you build, let's say that you want to build a prediction model. You want to predict the weather tomorrow. Right? What you need to do is become familiar with the data. How do you become? And I often say it's a little bit like a dating in the US. When you encounter data, at first glance, you will get a very superficial understanding of the data. You will see the most obvious features. very much like meeting somebody on the first date. I think somebody once told me some sociological or psychological research that said that people typically open up and tell really important things about their life or who they really are. But for that to be, it takes somewhere in the order of 40 to 50 interactions, right? If that is true, I don't know how true that is, but be as it is. With data, actually, a very similar thing happens. Physicists, and I suppose all scientists are familiar with this fact, that when you get data, you don't just say, okay, I got data and this is what I see. You keep mulling over the data, keep chewing on it for a very, very long time. You keep analyzing it. You do descriptive statistics, you univariate statistics, two variable statistics, and so forth. And the more you mull over the data, the more feeling you have for the data. See, data is produced because there is some underlying dynamics. Some force produces that data. Right? In the case of weather, there are atmospheric conditions, there are physics at play that is causing those particular values to happen. So there is an underlying dynamic which is latent, which you can't see. But the more you become familiar with the data, the more inkling you begin to have of what must be or what might be the underlying dynamic. Are we together? Then, one of the things about data is the visualization of data. It is always a good idea to do data visualization. Why should we do visualization is something we'll come to. But visualization is not just eye candy. It isn't that, oh, let's make a PowerPoint or a slide deck look prettier by making a few pie charts or bar charts and whatnot. The purpose of data visualization is to complete your understanding of data in a way that a statistical analysis of data will never help you do. And we will start with an example to make this point in a moment. Then, once you have become really familiar with the data, you will realize that the data comes with blemishes. It will have missing values. You need to do missing value treatment. For example, in a location, on that particular day, the wind speed equipment might have malfunctioned. So you don't have that value. But it doesn't mean that you throw away all other values, temperature, pressure, rainfall, etc., precipitation, for that location for that day, right? It just so happens that one attribute is missing in the data. So the question therefore comes, what do you do with that missing value? You have multiple choices. If you're data rich, if you have vast quantities of data, you're a data sheikh. You look at your spreadsheet and you say, I have so much data, I don't care. Then you could just drop that row, drop the data. That is rarely the case, especially in important domains like medical. It's rarely the case. If you look at the medical literature, you will realize that most papers are published on data sets that are laughably small, 20, 50, 100 records at most. Why? Ultimately, a lot of interesting diseases are they are treated by specialists. Those diseases, those specialists maybe see 100 interesting cases pertaining to something unusual they observed, and they are writing a research paper about it. Right? So there are many, many fields in which data is rather scarce and precious. So in that case, you can't just throw away a missing value from the data. Right? Then you also have to watch out. Can a piece of value, can a value in the data be wrong? A clue could be that it's an outlier, right? For example, you get your credit card bill, you have been doing your groceries and going to your coffee shops and so on and so forth, all the usual stuff. And then you find a $14,000 item for a cup of coffee. and maybe a bagel or something like that, breakfast. What does that tell you? Does it mean that you had a $14,000 breakfast that you have entirely forgotten about? That it is wrong. It's an outlier. It sticks out. And if you have owned credit cards, all of you must have seen in your lifetime an error like this, because at some cash register, somebody, right, instead of putting a decimal, forgot to put the decimal, right? Or something strange happened. So you need to look out for outliers, and you need to have a way to do outlier treatment. So those are the things that you should worry about, and there are techniques to do that. And when you get into the field in a more substantive way, then the entire books written quite literally on each of these topics. And just data analysis, there are countless books within data analysis. Just outlier treatment has enough number of research papers. Okay, so that is that. Likewise, data visualization, which often we trivialize as making pie charts and bar charts and scatter plots, because most people, that's what they do. It's not like that. Let me give you a sense of why visualization matters, and you'll see it immediately. Suppose I give you a spreadsheet of numbers. Within the spreadsheet, you can tell it's the numbers about the temperature, median temperature during the day at a location. And you see a pattern. You have to eyeball that spreadsheet for quite some time to realize that temperature has been increasing from January all the way to August. Median temperature let's say it's Fremont in the northern hemisphere, it would be the reverse in the southern hemisphere, has been gradually increasing all the way, more or less, going to August with fluctuations in between, and then trending downwards back to December, to lows in the December, isn't it? But it would not be obvious because data has other effects, random effects, such that some days are unusually hot in winter, some days are unusually cold in summer. As you know, there's a Mark Twain quip that said that the coldest day in his life, he said, was a summer day in San Francisco, right? So especially when there are fluctuations in the data, it is not so obvious to see what is going on. But imagine that you just plotted it out. When you plot such things out, it becomes dead obvious, isn't it? Am I making sense, guys? It does become dead obvious. Why is that so? I'll illustrate this with a point. See, when some of you are into hiking. I'm into hiking. Early in the morning, you go out hiking. I go when it is still dark. 5:30 in the morning, these days, it's still dark, it's winter. So you're walking. Then I like to see the beginning of a day, a dawn break. And actually, much of the fun is over by the time the sun rises. Right? All the colors, all the beautiful colors are way before that. So most of the time, I walk all the way to the bay along a beautiful creek. Right? So I'm enjoying the birds. It's a bird sanctuary. I'm enjoying the birds, the sunrise, or rather the colors in the sky changing, the stars disappearing, and so forth. My mind is on that. But suppose I hear a growl, right? And then I see right in front of me, let's say I see a mountain lion. Now think about it. A mountain lion, when you see it, do you start reasoning that, okay, the legs look about 2.5 feet long. There are 4 of them. Oh, it has a head. I think it's a head because I see what looks like 2 eyes in them. A nose. Oh, it even has a tail. Do you reason and then come to the conclusion it's a mountain lion? Or in the blink of an eye, you know it's a mountain lion and you're in a complete self-preservation mode. Now, what happened? Your reasoning capacity which is the capacity which you bring to bear when you do data analysis with numbers. It's your ability to reason, is of much more recent evolution. To the best of our knowledge, our ability to do abstract reasoning might be as recent as 100,000 years old. Let's be generous, give it 1,000,000 years in the human species, right? In the Homo, all of these things, Homo erectus, Homo sapiens, and whatnot, all the human subspecies put together, and obviously Homo sapiens is all we are left with today. Now, what about the eyes? Even little fishes have eyes. So, to the best of our knowledge, eyes have evolved at least 100 million years ago. If you think of eyes as learning things, things that are learning from data, that are figuring things out, what has happened to the human eye or to the eyes in us? It has been evolved to our high degree of capability over 100 million years of biological evolution, which probably explains why when you look at a mountain lion, you don't reason. You see a mountain lion and instantly you're in a survival mode, right? You're evaluating whether it's a risk to you or not, or whether it will leave you alone. Are we making sense? Now, I would like to illustrate this with a fact. Yes, so it's fun on the book, The Importance of Being Earnest, which I'm sure many of you would have read. This was a point that a great data scientist, or what used to be called statistician, Francis Escombe, made. This is a cautionary tale and really brings out the value of visualization and the power of visualization. People often say that visualization is just eye candy. Many data scientists even today, AI researchers say, visualization is eye candy, right? If the mathematical measures tell you something, listen to that. But is that sufficient? We'll explore it with the famous data set that Ascombe created. So look at this data set. There is X and Y has some relationship to X. When you look at this data set, and here I've given you the data, this is Python code. These are called lists of data. Values of X, and for every value of X, there is a value of Y, right? If you do descriptive statistics, and you can do that, given a data set, you can do a descriptive statistics. So this is a very common thing you do. You realize something quite interesting. I won't go over the code because at this moment we are doing very introductory stuff. Picking up pandas and NumPy, very admirable things to do. You must do that, essential qualities. But we won't have time for that here. But pay attention to what you see. There are 4 data sets. If you are told, look at the mean of X in each of the data set, the mean of X is, of course, because X is shared, is the same. The Y's were different, isn't it? You look at this Y here, you can tell that the Y's are different values, isn't it? Y1, Y2, Y3, they differ from each other. They're different lists of numbers. Nevertheless, when you pay attention to Y, all of those 4 data sets seem to have the same average Y value, mean Y value. The standard deviation of X is the same. The standard deviation of Y is also the same. The correlation between X and Y for each of the data sets is the same. If you build a linear regression model, that is, try to fit a straight line through the data, that's called what all of you must have done in school at some point, given a few data points, try to fit a straight line through it. The only trouble is sometimes there is no straight line that will go through it, through all the points. So you try to find the best line that you can nevertheless try to fit through the data, right? Leaving aside, that is closest to the data. That's one way of putting it. So when you do that, a line will have a slope and an intercept. Look at the slope and intercept for all of these. They look almost exactly the same, isn't it? Up to many decimal points. And your model, the explanatory power of or how much errors your model is making in explaining the data, it is called R squared, or the more formal term is the coefficient of determination. We'll come to it shortly when we do regression. And the sum squared errors, they all match. Looking at this, would you agree? Would you not have the feeling that these four data sets must be identical or nearly the same? Would you agree, guys? You would agree that this probably is coming, it's alike, same data is being described, or very similar data is being described. Or a more formal way of saying it is that they have been sampled off the same behavior data, some same data pool, right? So, and you can build a regression model that says y is equal to 3, intercept is 3, and slope is half, 3 plus half x. You would make a model like this, isn't it? You say this describes the data. Now, let's go and see what is the reality, though. Look at the four data sets now. And when you view it visually, what does it tell you? Are they the same data set? Do they even seem to come from the same pool of data? Not at all. So what has happened? The aggregate statistic, remember, is an aggregate measure over the instances. And it is never, it wasn't enough to tell you the whole story in the data. But the moment you visualized it, you could see the whole story. And therefore, the importance of data visualization. I'm trying to bring out the point in many ways. Even basic histograms, you will see all of them are different. I won't go into it, but there is a more fun data set. Someone created, actually took pains to create a data set. So imagine that you have 13 data sets. One of them, when you plot it in XY, it looks like this. What does it look to you like? Dino, right? But then when you look at it, the same 13 data sets, you notice once again that all of these data sets have exactly the same mean, right? For X and Y, the same standard deviation, pretty much the same correlation. And you might think that they are all the same. So if the first one looks like a dino, you would imagine that the rest also looks like a dino, right? Or if not a dino, maybe a horse or a dog or something like that. Right? On the other hand, when you visualize the data, this is what you see the remaining 12 data sets looking like. None of them remotely look like a dino, right? And do you realize that you can spot it immediately? Instantly, you can look at it and tell that this is not, all of these data points are vastly different. And therefore, the value in data visualization. So I will end the topic of data visualization because I want to get to the machine learning part with an interesting story, if you will allow me to tell a story. Any questions, guys, here before I move on? By the way, all of these notebooks will be on the course portal. Anyone, any questions before I move on? Okay, then I'll move on. So this fascination with data visualization has become a big subject, and it has an interesting history. I suppose it depends upon how you describe visualization. Even in caves of ancient civilizations, you see some depiction of reality, some data, right? You often find marked onto bones, little marks of how much something is or isn't and whatnot in shapes. But generally, when we talk of data visualization, because we need a starting point, we often take the life of a remarkable lady. Well, many of you may have heard the story of Florence Nightingale. How many of you have? Oh, not many. Oh, okay. So in that case, I'll tell the story of Florence Nightingale. The story goes, and we are sort of taught, if sometimes you read it in books when you are a kid. She was a remarkable lady born to British aristocracy, but very idealistic. And one day she was sitting under a tree in her garden, and she felt a calling, in some sense, that she should give her life, dedicate her life to a higher purpose, unselfishly. It apparently, the way I heard the story, something asked her, "Are you willing to do it unselfishly?" And she said yes. And the only trouble is, what was the higher calling? Wasn't told, right? So she traveled the world. She had a quality about her. She carried a diary, and whenever she would notice something, she would not just describe it in words, but actually write down numbers, convert it to data. As you know, at this moment, there is a war going on between Ukraine and Russia. It turns out this war seems to be an endless thing in history. Crimea, one of the bones of contention between the two things, was a bone of contention in 18, I believe it's 1851 or something like that. At that time, the Crimean War, so-called, was going on. Russia on one side, the Western powers on the other. Does that look reminiscent of today? Right. So as that was going on, she went there and she saw a lot of suffering. Given her nature, she put up a tent squarely in the middle of the battlefield in one side, right? And opened it to the soldiers of both sides, right? Without partiality. And people loved her. As she was caring, and she was called the Lady of the Lamp, and she would roam around till late night when everybody would be asleep, helping people, helping soldiers and whatnot. But she was also a person who gathered data. As she gathered data, she came to a startling discovery. She had only 23 rows of data, but she came to a most startling discovery. And she said that, see, what I find is a battle wound is the least likely cause of death on a battlefield. Isn't that a remarkable statement? From her data, she noticed that a battle wound is the least likely cause of death in a battlefield. And it's a very surprising thing. So she made a visualization, which I'll show you, which is historically the famous two roses visualization. She went to the Queen, returned when the battle was over. She went to the Queen of England, made a point, showed. Now, you see, when you talk to the Queen, it's never a good idea to come up with long mathematical equations, but to make it very visual, universal, appeal to everyone, you're talking to the thing. And I believe it was Queen Elizabeth at that time. She argued for, and by the way, the largest cause of data was that death was a poor hygiene. Like when you got sick, the environment, when you were taken care of, there was nursing as a subject did not exist. The people, when you got sick, they were physicians, but physicians wouldn't nurse you. They would just give you a diagnosis, right? And say, take this medicine. Remember, these were the days before antibiotics or any of the modern medicines that we know of and trust today, right? So the medical science wasn't advanced, but nursing did not exist at all. So prisoners would be called in to nurse. Sometimes some beggars would be tempted with little bits of money to come and nurse or take care of the sick. And she went to the Queen and made a statement that, see, we need to rethink everything, right? We need to create what she called nursing, special modern institutions of nursing, where hygiene and cleanliness are the primary drivers. When people get sick, even as vital as it is to give them rest and medicine, is to keep them in a sterile, hygienic, clean environment. So with one visualization, she founded two subjects. she quite literally founded the entire field of nursing, modern nursing. Modern nursing today, we say, began with Florence Nightingale because she was granted uh, funds to create a hospital, the first modern hospital. So I suppose in contemporary Silicon Valley, it would be like one of those AI founders rushing and coming back with $1 billion in funding, right? For some idea of his or her. So, well, that's one thing that started. The second thing that started is people realize the value of data visualization. And I would like to show you that visualization just to button up the topic of visualization and then move on to machine learning. So obviously it's a big topic, but I think I do have the Florence Nightingale's visualization here. And the only reason I mention it is to bring home the point that do not underestimate the value of proper data visualization. So this was a hand-drawn visualization that she came up with. If you look at this visualization, the, the things that you see in pink or pinkish is the death from battle wounds. Do you see that at any given thing, let's January 1855 or any one of the sectors, it is a pretty small proportion of the actual casualty, right? And when you look at this visualization, would you have any doubt after this about the point she's making? Right? It becomes visually obvious and incontrovertible if the data is correct, isn't it? So this is the famous two roses visualization. We also give a free and a course on data visualization in which we challenge you. So when people look at these kinds of visualization, they say, okay, it is hand done and handwritten. We can't do it with basic tools. Right? In the world of Python, the most basic data, what people call basic, and I don't, I think it's pretty powerful, is matplotlib. How many of you are familiar with matplotlib? Many of you are, right? But then there's other things, Seaborn, Plotly, right? And whatnot, Altair, etc., etc. You could use that. So one of the things we sort of bring home is that it is not the tools, it is a systematic way to reason with data that leads to good visualization. So we challenge, can you take just matplotlib and recreate this? So the first thing is data is very simple. Actually, when you look at this data, you won't believe that the world was changed and modern nursing was born out of this 24 rows of data. This is the data that she took down in her notebook. It is the statistics of death every month and from the different causes. So the first thing you would do is you would make a bar chart like that. This is, how many of you have been used to making bar chart like this when you see data like this? Isn't it? You would do this. Now, how many of you feel that this is absolutely evocative visualization, your bar chart? Right? So sometimes, you have to make a visualization evocative to tell a story. People often say in communication, you not only need logos, the intellectual part, you also need pathos, things, that create an emotional connection. And so you would agree that this is a lot more appealing, right? Though it says the same thing. One of the things we do is, can we recreate it? And of course, that's again a free course. Watch out for it. One of these days, we'll again offer it. And at the end of it, with just a little bit of systematic thinking, and that's what we teach you how to think, we come up with this. This is coming from our Python code. Would you agree that this is a pretty close approximation of the two roses? Right? So this is, and compare it to this. Look at that. I'm just putting them side by side for you to compare. There we go. One more, shrinking. Yes, look at this. And so the point that I'm making is, this field of data science, every aspect of this is fascinating. Data analysis, they're clever tricks to rationalize the data, vectorize the data, and make it into tidy data. Data visualization, again, a beautiful subject. enormous number of PhDs have come out. And every time you think the last word has been said, somebody writes another PhD and completely opens new field. In fact, there is an entire field that came out called computational art, right? From a MIT PhD. And if you want to see, go and look up processing.js. Right? Visualization has its own theories. It is a visual language, just like textual language has a grammar to it. Right? You wouldn't be able to communicate in a language unless it had structure, it had grammar. Because grammar facilitates the ability to craft infinitely many statements, sentences to convey what you are saying and nevertheless be understood. In the same way, in visual, we look at visualizations as a visual language these days. The AI in particular, some of the state-of-the-art models we have, they are visual language understanding models, vision language models. Are we together? They literally are called VLUs. And now we are in the world of multimodal languages, multimodal models that jointly understand sound, video, audio, images, text, right? Everything together, it can jointly understand, even thermal images and depth images and normalizations, like in which direction, perpendicular direction of a shape, right? Things, if you, any one of you who have taken courses in computer vision would know. So these are all the different kinds of data you can gather. And today, the state-of-the-art AI models that we have can jointly understand all of these as one unified, in some sense, language or expression or ways of saying something. And it is intuitive. If you open a technical textbook, what do you say? You often see on a page, there'll be a picture of something, maybe a machine part. There will be some diagrams and graphs, right? There will be a mathematical equation and there'll be running text. And all of them collectively and jointly and in collaboration are trying to convey something to you, communicate something to you. Isn't that? And that is literally multimodal communication or expression or language. Right there, there's text, there's image, these two are there. Well, you don't have video on that page or audio, but it is the simplest form of multimodal that you can see. And that's a reality. Technical textbooks are all like that. That is where those are the things you learn in our formal course, which will start in February, but not this course, obviously, will, in the spirit of crawl, walk, run, let's be kids and learn to crawl and walk in this course. So that is so much for data visualization. Now, all of these notebooks, guys, as I mentioned, my team is going to post to the course portal. Play with it and have fun with the code and take the code and use it, of course, do whatever you want with it. I will now come to what will be the remaining part of this course, namely machine learning or artificial intelligence. Before we go into artificial intelligence or machine learning, which will be, as I said, the remainder of this course, starting from now. All right, guys, so now that we have looked at the data proper aspect of it, that you need to analyze the data, you need to wrangle the data, become familiar with it, and visualize the data. A simple way of putting it is that, guys, and I always put it a bit, I don't know, I hope it's not offensive, a bit humorous perhaps. It's like a date, right? You want to know a human being, you want to become really best friends with somebody, you need to spend a lot of time with that person to be the best friend. People don't become your best friend in the blink of an eye, right? Or maybe sometimes they do, but generally not. In the same way, data analysis, data, when it comes, spend a lot of time doing what is called exploratory data analysis, EDA. And part of it, a significant part of it is statistics, but also a significant part of it is data visualization. Data visualization is not just eye candy, it has more importance. And we went over that. That's a summary of what we were doing a little while ago. Now I'm going to go to the next phase. Imagine that you have data all cleaned out. You are trying to do some machine learning on it. So we will take up the topic of machine learning and AI. Again, today is an unusual session. Of the 5 sessions today is high-level ideas. From tomorrow, we'll do more code, practical code. So if I were to ask you, what is artificial intelligence? What defines artificial intelligence? It seems to be the buzzword everywhere. It's hard to look at any news without AI there, or any social media without some chatter on AI, right? AI is supposed to destroy the world. AI is supposed to bring about the next heaven on earth, right? Is going to take away all our labors, right? We won't, the humanoids will come and mop our floor and vacuum our carpets and clean our dishes and do everything for us. The humanoids are going to come and kill us. Reminds me of Dickens' Tale of Two Cities. It was the best of times, it was the worst of times, right? And so it has always looked throughout history. So today is no special, but no different, though it seems to us like that. But so let us focus first, before we worry about whether AI is for good or for evil. Let's ask ourselves, what is artificial intelligence? It is 2 words, artificial and intelligence. So let us try to unpack the 2 words. The word artificial comes from artifice. What is artifice? Artifice is something, a creation that is not natural. For example, a plant grows, a seed turns to a plant. That is not an artifice. That is natural phenomena, right? Clouds wander into the sky, that's natural. But you build something with wood, a table. A table is an artifice, isn't it? It is an artificial creation. So whatever we say is artificial, we mean it has been created. It is a human creation. Now, let's go to the word intelligence. What is intelligence? Intelligence is one of those words that's far easier, we think, to understand than to explain, right? So we often colloquially say, oh, that guy is intelligent, or that girl is super smart, and so on and so forth. We use such words pretty loosely. What do we mean? Besides the fact that most of the time we are wrong in saying that, because most human beings are intelligent and super intelligent at something. It's just they differ from person to person what each person is super intelligent at or super smart at. My personal perspective, for whatever it's worth. But let's go back to the idea. What is intelligence? Would anybody like to volunteer a meaning to intelligence? Go ahead.
So it can have multiple attributes. Being at that moment, somebody being able to respond, right? The right answer. I may be knowledgeable, but if I'm not able to speak at the moment.
So a camera at a traffic intersection is always present. It's always looking at reality. It's not lost in thoughts. Would you call it intelligent?
But if I ask a question and you give the right answer, I will say.
But
yes,
there are many people who cannot speak.
Okay, but that is one attribute that I said.
No, you're heading in the right direction. You're making good progress. Please continue.
So second attribute being you have a lot of knowledge, and you are able to identify a pattern and give a solution. So for us, it's not obvious, but for you, it's obvious, and you show us.
You can do pattern recognition. Very good. It's a mark of intelligence. Right?
Which came in my
mind. Anybody else? That is a good characterization.
Yeah.
So guys, go ahead.
Yeah. Ability to convert data into information and information into knowledge.
That is, see, to convert data into information, it just means cleaning up the data. To convert that into knowledge is predicated. See, the word knowledge, if you look at the root of it, it is to know. To know often has a sense of recognition. Suppose you meet the first time in your life, you see a cow, you don't know what it is, but you meet a lot of cows, and then you have a recognition. There's a memory part, and you say, well, now it is exactly like all those other four-legged, one-tailed creatures that I saw, isn't it? So knowledge often has a memory component and is in itself memory. I would say to convert data into knowledge is perhaps a little element of that. I wouldn't go too much. It's structuring. It's about classifying. Maybe there is some intelligence required, fairly low. Any other definitions of intelligence? It is right, Sudhindra, but a little bit more I wouldn't probe it.
To respond.
I think intelligence is ability to learn, reasoning it, and
You
maybe.
hit it, Musa. Musa,
Yeah.
you got it right. See, it is the ability to learn. For the longest time, people have thought, and this is the history of AI, when people try to create artificial intelligence, it has been the millennial dream of humanity. We have always wanted to play gods. We feel that gods created us, and most people believe that to be the truth, though a very small minority believe the other way is more likely, that we created gods, because the last we checked, monkeys and elephants don't believe in gods, to our knowledge. It's human construction. So there are arguments both ways. But let us say that God created us. Then we would like to create also intelligent beings. So in every culture, you find narratives of human beings somehow magically creating intelligent life forms. In the Hebrew culture, there's a concept of golem, that you can take a piece of clay and you can mold it into a form, perhaps a human form. And if you're really wise and a rabbi of high caliber, you can breathe life into it, and then it will come about. Except that beware, it will do whatever you say, but beware of the dangers of that. And in such stories, already you see a resonance of today, where we are scared of AI. We are creating it and also getting scared of our own creation. When we think of Aladdin and his magic lamp, what comes out of the magic lamp? A jinn. And jinn does whatever you ask it to do. It seems that we have created artificial intelligence in a story form. So in every culture, you find that for thousands of years, in some subtle form, there is a human aspiration to create intelligence. People have, as computers evolved, Alan Turing, he wanted to solve, as far as I can make out, the enigma by creating a universal machine that could think. Didn't quite. Charles Babbage, in the world way before electricity, I suppose, or way before electronics, was trying to create a mechanical computer. Ada Lovelace was creating the first programming element for it, programming for it. That's how programming was born. Ada Lovelace being the sister, I believe, of sister or daughter of Lord Byron or something. What's the history? Lovelace was.
This is the daughter of the poet Byron.
Lord Byron, daughter of Lord Byron, yes. Okay, so she had the insight to realize that if you want a machine to do general purpose and many different tasks, you need a way to encode instructions for it to follow. And thus programming language was born. But even then, people were dreaming and wondering if through this instructions, you could have general purpose instructions so that the machine could achieve some form of generalized intelligence. When 1950s, when the whole with the landmark AI conference, and where the McCarthy created the term artificial intelligence, the dream has been there to create artificial intelligence. When people thought of artificial intelligence, they would think of thinking machines. There was actually a company in Silicon Valley called Thinking Machines, a high-flying company that didn't succeed. Later on, broke up, and one part went to Oracle, another went to Sun, if I remember right. Now, thinking has a problem. If you say that intelligence is the ability, a mark of intelligence is the ability to think. So, for example, this particular pencil is not intelligent because it doesn't think. We think. So, therefore, we are intelligent. That's a differentiator. What's the problem with that? The problem that comes is thinking is not measurable. We don't even have the vaguest clue how to quantify thinking, isn't it? That's a problem. But as one of you, I think it was Musa who said that another way of thinking about intelligence is to say it is the ability to learn. So the question comes, is learning measurable? So let me give you a story and you tell me. Imagine that you take some children, or one child, doesn't matter, to the zoo. And let's imagine a simplified zoo or a meadow. In the meadow, there are some cows and there are some ducks. Right? There's a little pond and there are ducks around the pond and there are cows there. And this is a 2-year-old child and you're trying to tell, you look at that feathery little creature, that with webbed feet and a beak is a duck. And the 2-year-old is getting lost and confused with all the attributes that as parents we all over eagerly try to teach the kid. Right? Then we show the big cow and say, look at that big thing with 4 feet and tail and swishy tail and horns. Right? That's a cow. After a little while, you want to check as parents that did the child learn? So what you would typically do, you could do one of two things. You could go back to one of the ducks that you showed or cows that you showed and ask, what is this? Now, one of two things can happen. The child can either get it right or be wrong. So how would you know that, suppose the child was correct? Would you therefore have said that the child has learned what a duck is or a cow is? Why not?
It may forget tomorrow.
No, that's all right. You can always unlearn. But why not? Because you showed an example. You went back and verified against a cow and a duck that you have already shown. What if the child has memorized it? Right? What if the child has eidetic memory and does not understand what cow and duck is, but remembers this specific thing is a cow, this specific thing is a duck? What you need to do is show another duck which looks different in subtle ways from the current ducks, and yet another cow, because all cows are different from each other in some ways, and ask what those are. If the child gets it right, then you may have a sense that perhaps the child is getting the hang of it, isn't it? But it is still a perhaps, because the child may be just guessing. Right? Guys, this is a fact. All of you have been through education. What do you do when you don't want to learn a subject? All of you have had this experience. You hope that the professor repeats the questions from the previous year on the exam. So you get this so-called question bank of important questions and you memorize the answer to them. And you go into the exam hoping at least some of them will come and you'll pass the exam. Right? Isn't that true? Right? That is clear evidence that it is not learning. And therefore, you need to verify that it isn't memorization. Remember, memorization is the converse of learning, in the sense that learning is the ability to generalize from examples. Right? So you see a few ducks and cows, and you get the sense of what a duck is and what a cow is. Are we making sense? You get the cowness of a cow in some sense, or the duckiness of a duck. What is the essential quintessence of those animals that makes them what they are? And when you understand that, then for all the cows and ducks in the world, you'll have correct identification. Does that make sense? So now comes this thing, the child may still nevertheless be guessing. So what you show is, you show a lot of examples of cows and ducks, unseen examples, and you see how well the child is doing. Now what can you do? You can measure, you can keep track of how many times she got it right. What will happen in the beginning, when the child hasn't learned it and is purely guessing, there will be a pretty high error rate in her identifications of cows and ducks. Does that make sense, guys? Huh? You have no idea. So anytime you say cow or duck, whatever you feel like. And so you'll be quite often wrong, and there will be a baseline error rate of guessing. But as the child begins to get a sense, and she is beginning to identify the cows and the ducks, her error rate will slowly go down. Perhaps she will identify ducks a little bit better than she can identify cows or whatever it is. And her error rates will go down in a measurable way, isn't it? And therefore, if we defined that learning is a process of generalization from examples, right? Because you form the concept of what a cow is or duck is. It's a generalization from examples. Then learning is quantifiable. In this particular case, you can quantify whether learning is taking place or not, and to what extent the learning is taking place, isn't it? Are we together? And therefore, intelligence, the only way we know is to identify or quantitatively say that a measure of intelligence is learning, that learning is taking place. Now, when it comes to learning, comes the big question: do only biological systems learn? Or is learning something more universal than just carbon life forms? Because the way we quantified learning as a reduction in errors, nowhere did we mention carbon life forms. It's a mathematical definition, isn't it? And so you can ask this question: can we make machines learn? Can we make the machines learn? And it turns out that you can make the machines learn as much as you can make humans learn. The discovery of this is there are two steps to it. One is to properly quantify errors, right? And its generalization is something called a loss function, but let's just use the word error. The first person who did that was the son of a coal miner, and the father was very concerned that you should just join the family tradition of working in coal mines, where the kid had different inclinations. And his school teacher noticed that inclination and took him and made him into more of a student who went to university. And he wrote what is today we would call the first loss function. It is called sum squared error. And I'll explain what that is, but it's a measure of errors. Can you guess when that happened? Was it in 2005, 1990? When was it?
1910.
1910. Oh, wow, that far back. Okay, brave guess. Anyone else? It was 1793. And the story is very interesting. And today, of course, I'm giving a general sort of introduction to stories. So there was a competition in Europe. There was some planetoid or planetary heavenly body that was behind the sun, and you had to predict when will it show up in the sky again. I believe it was the Ceres, but I may be wrong. When will it show up in the sky? So, and where will it show up? So now, if you have ever lay down on the ground and watch the skies, you realize that the sky is vast. Anywhere it could show up in the vast sky. And on any day, you have no idea. Any month, any year, any day, it could show up. And you had to make a prediction. So that was a grand challenge in Europe. So the tradition in Europe was to patronize the development of mathematics and science through grand challenges, very much like the Netflix prize and so on and so forth. The tradition is still alive. So many people submitted, and one of the submissions came from this mathematician. Okay, have you guys guessed the name of this mathematician yet? 1792. It was Carl Friedrich Gauss, who is often called the Prince of Mathematics. So he submitted a paper, he wrote a paper, and he gave a prediction of where it would be. And it was so far better than everybody else's prediction that the next best prediction was widely off, right? And so, but problem with Gauss was, Gauss being Gauss, he was rather wily. Once he was asked, what's the definition of genius? He says, never to show your hard work and to wipe out the trails of your work and just show the results. And if somebody asks, how did you come upon it? I'm paraphrasing. You'd say, well, it's easy and obvious. And the other people will then sweat on it and realize to them it's not so obvious. Right? It's a converse of what happens in corporate America today. Even if you make the tiniest progress, you felt impelled to walk into your manager's room, right, office, and make sure he recognizes you made this tiny progress. Anyway, Gauss being Gauss, he was rather coy about how he did it. Then in 1805, Legendre, another great mathematician, wrote a paper, Method of Least Squares, literally on that. And then Gauss came out of the woods and said, now wait a minute, I did it first. Today we know both of them independently did it. And actually there was an American also who did it at the same time. So I'm giving you the history and taking you on a detour simply to tell you that this field has deeply human roots. They're very interesting characters. They're people with great passion who have built up this subject. It's not a dry, mathematics is not a dry subject. It's one of the most human and intense subjects you can imagine. So, well, and anything as profound today as AI, which is changing the world every single day, right? Today, I'm told, I'm not much of a stock market person, I'm told that today, because of a development in AI, the US stock market moved by $1 trillion, which is probably the GDP of dozens of countries put together.
It is Spain.
Was it?
$1.5
Spain.
trillion.
Wow. So AI is having profound effect on everything in life. Today, social media is driven by AI. Intelligent cities are driven by AI. Everything, whether you know it or not, is there's AI at some point, some machine learning somewhere. You just don't realize it. So these subjects have deep roots going back hundreds of years. So never believe that everything started 2 years ago when the large language model came on the scene. Right? These things have deep, deep roots, this subject. Obviously, there are big discoveries, big breakthroughs that accelerate all of it. 2 years ago, there was a huge acceleration to its great credit, but it's a deep subject. So now we agreed that learning is something you can quantify learning. It's people often call it the error function, the objective function, the loss function, utility function. There are subtle variations between them, but for the sake of this introduction, we'll gloss over all of them and just use the term loss function. Think of it as some way to measure errors and then have a few other things added to it, but it's a way of quantifying errors. Are we together? So then within that machine learning, there are three core sort of the subject, I would say bifurcate, but bifurcation is partitioned into two. But yeah, let's take the first great bifurcation. The first bifurcation is whether you teach a machine by showing it some examples and answers or whatever, right? Or giving it data and making it do pattern recognition, find patterns in data, that's one way. And or through trial and error. You tell the machine, I'm not going to tell you how to do it at all. Just learn from trial and error. Every time you make a mistake, there's a penalty. Every time you get it right, there's a reward. Now, it is very remarkable that machines can literally learn from trial and error, and given what is called a reward function, it figures out how to do it. And there is a video that is interesting enough that I would like to show you. So humor me, I'm going to play this little video for just to show you the power of this form of machine learning, which is called reinforcement learning. By the way, the breakthrough of last week that has turned the world upside down, reinforcement learning had a huge participation in that breakthrough. So let's go in here and see what is it about.
OpenAI built a hide-and-seek game for their AI agents to play. While we look at the exact rules here, I will note that the goal of the project was to pit two AI teams against each other and hopefully see some interesting emergent behaviors. And boy, did they do some crazy stuff. The coolest part is that the two teams compete against each other and whenever one team discovers a new strategy, the other one has to adapt. Kind of like an arms race situation, and it also resembles generative adversarial networks a little. And the results are magnificent, amusing, weird. You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and semi-random movements, the seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the seekers by blocking the doors off with these boxes and started winning consistently. I think the coolest part about this is that the map was deliberately designed by the OpenAI scientists in a way that the hiders can only succeed through collaboration. They cannot win alone, and hence they are forced to learn to work together, which they did quite well. But then something happened. Did you notice this pointy, doorstop-shaped object? Are you thinking what I'm thinking? Well, probably. And not only that, but about 10 million rounds later, the AI also discovered that it can be pushed near a wall and be used as a ramp, and ta-da, got him. The seeker started winning more again. So the ball is now back on the court of the hiders. Can you defend this? If so, how? Well, these resourceful little critters learned that since there is a little time at the start of the game when the seekers are frozen, apparently during this time they cannot see them, so why not just sneak out, steal the ramp, and lock it away from them? Absolutely incredible. Look at those happy eyes as they are carrying that ramp. And you think it all ends here? No, not even close. It gets weirder, much weirder. When playing a different map, the seeker has noticed that it can use a ramp to climb on the top of a box, and this happens. Do you think couch surfing is cool? Give me a break. This is box surfing. And the scientists were quite surprised by this move, as this was one of the first cases where the seeker AI seems to have broken the game. What happens here is that the physics system is coded in a way that they are able to move around by exerting force on themselves, but there is no additional check whether they are on the floor or not, because who in their right mind would think about that? As a result, something that shouldn't ever happen does happen here. And we are still not done yet. This paper just keeps on giving. A few 100 million rounds later, the hiders learned to separate all the ramps from the boxes. Dear fellow scholars, this is proper box surfing defense. Then lock down the remaining tools and build a shelter. Note how well rehearsed and executed this strategy is. There is not a second of time left until the seekers take off. I also love this cheeky move where they set up the shelter right next to the seekers, and I almost feel like they are saying, yeah, see this here? There is not a single thing you can do about it. In a few isolated cases, other interesting behaviors also emerged. For instance, the hiders learned to exploit the physics system and just chuck the ramp away. After that, the seekers go, what? What just happened? But don't despair, and at this point, I would also recommend that you hold on to your papers, because there was also a crazy case where a seeker also learned to abuse a similar physics issue and launch itself exactly onto the top of the hiders. Man, what a paper. This system can be extended and modded for many other tasks too, so expect to see more of these fun experiments in the future. We get to do this for a living, and we are even being paid for this.
Isn't that the fun part? In AI, you do all this fun stuff for a living, and then you get paid one of the highest salaries in the industry. So, I hope, guys, you get a flavor of reinforcement learning. Let's do an example. In this, you don't tell at all what is the right way to, how do you learn? You don't tell it at all, how do you learn? You just say, go, keep figuring it out. And isn't it amazing what things it figures out? Many of the things go beyond even what the scientists would have expected. This is the beauty of reinforcement learning. What you saw, this is a very old paper. This paper came out, I suppose, I forgot. I've been showing this paper to people, this video to people, to many batches for a very long time, 5 years ago. 5 years ago, right? And today you hear of the great breakthroughs that reinforcement learning is making. So that is one way of teaching machines. Just give it a reward. And the opposite of reward is a penalty. And you teach it through that. And it figures it out. The most amazing thing is that it figures it out. And sometimes it figures out things that you wouldn't have imagined. That is one form of AI. The other form of AI are called what is often called supervised learning, though I'm not too fond of the word. Let me just call it predictive modeling, or making models that predict something. Are we together? That model that predicts, we can write it like this. You do this. Suppose you have data. Suppose you have data, and the data, is my screen still shared? Oh, it is. And let me go here and here. So suppose you have data like this. You have X and Y. I'll just take one dimensional, like one variable. And there's some values. The X values, let's say, are numbers, right? So let's say that this is, I'll take an example. Let's say that you're a young entrepreneur and you get it into your head that you need to sell ice creams on a beach. So you dream up of opening a shack, ice cream shack. Now, ice cream has a problem. Let's make it concrete. You buy ice cream from a wholesaler, right? Because you're not likely to make it at night at home. Or maybe you do, but the fundamental problem is you need to guess how much ice cream you're going to sell tomorrow. If you underestimate the ice cream, then the kids will come, they won't find ice cream, they won't be happy, and they'll never come again. If you overestimate how much ice cream will be sold tomorrow, what will happen? A lot of ice cream will go waste. It's a perishable thing. The wholesaler is not going to take it back, right? So let us say that you need to estimate the right amount of ice cream. You figure out soon that, see, the ice cream that sells depends on temperature. Let's say that X is temperature and Y is quantity of ice cream sold. So far, so good, guys? Suppose you're in this situation. So your target variable, so suppose you have a temperature, 72 degrees, and a certain amount of ice cream got sold. Let's say 25 units of ice cream were sold. The temperature goes to 90 degrees and you happen to notice that more ice cream got sold. Let's say 40 units were sold. And let's say that there was a very cold day, 40 degrees, and then you notice that maybe 6 units of ice cream were sold because there were hardly any kids on the beach. Right? So now what has happened? You are looking for a relationship. What are you searching for? You are saying that somehow you need a function. This is what you are searching for. And you make predictions wear a hat in machine learning. So you're trying to predict how much ice cream would be sold given temperature. You need a good function. It could be a straight line or it could be anything, right? Let's say that your data looks like this. This is the temperature and this is ice cream. This is your Y, this is your X. Let's say your data looks like this. What is it? I'm just cooking it up. I don't know if this is a reality or not. But let's say that you have, what you're trying to do is fit a function like this to it. So this red line that you just drew, this curve that you just drew, is the function that you want the machine to discover. Now you may say, well, no, wait a minute. How do you know that that is correct? Right? And the answer in machine learning is that you don't need to know. There's a paradoxical statement by Box, a great data scientist, who said, all models are wrong, but some are useful. What did he mean by that cryptic statement? What he meant is that, see, when you get data like this, you're seeing only a part of reality. For example, you don't see the effect of wind on a very windy day. Not many kids may show up. You don't see how much rainfall is taking, precipitation is there. On a rainy day, less kids are going to be on the beach, isn't it? Or maybe less inclined on a windy, cold, windy day to come to the ice cream shack. There are many other factors that may be there. At the end of it, you don't know the complete underlying reality, but you don't need to. Your practical need is, from the perspective of the ice cream entrepreneur, to get the best prediction you can given the data available to you. Are we making sense?
Yes.
You just need a model that works, a function that works, because the underlying true function may be, for all practical purposes, unknowable, and it doesn't matter. From which the statement that all models are wrong, but some are useful. That is true, by the way, of more broadly of science too. The laws of physics, for example, gravitation, the gravitational equation of Newton, force is proportional to the two masses and inversely proportional to the distance between them. We all learn about that. Is it true? Well, it works on Earth, right? It is useful. Like if you, for all sorts of mechanical engineering tasks, you better use that, right? But is it true? We know it is not true. Right? Einstein's theory of gravitation, general relativity, makes a very non-trivial correction to it. But that correction is not relevant to us unless you're looking at large distances, right? For example, if you're launching a satellite, then you need to know the Einstein equation, right? But you don't need to know it on Earth when you're doing engineering, buildings, and so forth. Right? So you go for models that work. And the laws, now you can say, okay, now maybe Einstein's theory is right. I can assure you as a physicist, we know it for a fact that it's not correct. That too is a model that works. But we know that it has to be wrong because it doesn't reconcile with, well, quantum physics. Right? And quantum physics itself cannot be correct because it doesn't reconcile with relativity. Right? So at any given time, people, and nevertheless, the very fact that you have computers, the very fact that each of us, we are having this conversation and I'm writing on this digital pad, means the semiconductor technology works and internet works. And that works based on the quantum physics that we take for granted. It doesn't matter that in a more fundamental sense it is wrong. And we don't know what the right theory is. What matters is it works and it creates a technological revolution that we all depend upon. Right? That flavor you see throughout machine learning. You are always in the pursuit of a model that works. Never ask the question, is this the correct model? But is it a valuable model? Right? So again, this process. So now I'll summarize it like this. When you have a box, imagine that data goes in, and now I can complicate this and call it x2. X1 could be, let us say, wind speed, windiness or wind speed. Now there are two variables. You could be even more accurate and you could have three variables. And so you could have n variables that you're using to predict the amount of ice cream that you sell, amount of rainfall, right? Now, some variable, now here's the paradox. Sometimes you know that not all variables are useful. For example, let us say that in the data, day of the week matters. Kids are brought to the beach by their parents. Parents are working during the weekday, right? Holidays they bring in, all of those matters. But does, for example, the number of penguins who jump off some island in Antarctica on that given day, if you just happen to be given that information as one of the columns here for penguins, would you know if it matters? And how would you be sure that it doesn't matter? Somebody thought it relevant and gave it to you, the answer to that is you don't know. You assume that everything could matter. You build a model, and a posteriori, you let the model tell you that it doesn't matter. The penguin was not, penguins jumping off, into the water in Antarctica. It turns out doesn't really matter in predicting how much ice cream this entrepreneur will sell on a given day. Right? So it is only after the fact that you discover. So that is the journey of learning. When you build models like that, it not only helps you build a prediction model, but it also helps explain what really is going on, right? So this thing, let me just call it y hat, when it is some mathematical function. And when y hat, I will write it in mathematical notation, is a number or a vector. It's a number, a measurable. Like, for example, 25, 46, these are numbers. This particular kind of models, AI models, there is a name for it. These are called regressors. These are regressors. And this activity of building, or this technology or this technique of building good prediction models where you predict numbers is called regression. Now, I took a toy example. Let's make it very real. If you're predicting next year's GDP based on all sorts of economic variable, that's a number. You're trying to predict what the weather will be tomorrow, which is there's an entire department that does that based on thousands of factors and huge amounts of data. Those models are regressors, isn't it? They're regression models. Whenever you're predicting a number, it's regression. Then you have something else, which is not regression, but a different flavor of prediction you make. And let me bring that about. So suppose you're given certain attributes of animals. For example, that meadow. Let's go back to the example of kids trying to tell whether something is a cow or a duck. And let's take two attributes. X1 could be the size of I'll just use the word size. Think of it as volume or whatever you want to think of it as. X2 as, let us say, the weight, how heavy the animal is. And what you have to predict is cow or duck. Right? So y hat is to give the answer cow or duck. Are we making sense? So now, suppose you're given some number and you say cow and something you say duck. What are you predicting? Or what are you're predicting a
Yes, on binary.
binary, or you're identifying, right? So this is called this sort of activity when you have to identify from a limited set of choices. Remember, identify from a limited set of choices. It is called classification. This is classification. Why? The word comes from the fact that, see, cow is a class. In other words, there's so many cows of different kinds, but they all share a certain set of attributes. So classes are cow, duck. In this case, there are two of them, which is why you would call it a binary classification. But suppose I threw in horses also. Now you call it multi-class classification, right? Does that make sense, guys? And so you have to tell what. Now, here's the thing. You must a priori tell what your classes are. You cannot say that I won't tell you, you just figure it out. No, it doesn't work like that. Why does it not work like that? Because when you ask the machine to learn, how will the machine learn? It learns from data. So what you do is you give it some real data. It's called the training data. So here is what you do. And that is why this is called supervised learning, because just like you would do as a teacher or as a parent would do with a child, first give some examples. Say, this is a cow, that is a duck, isn't it? What are you doing? You're giving some real data where the answers are known, the labels are known. These cow ducks are often called the labels or the classes. They are known associated with this particular thing. You show some examples and you learn from examples. That kind of learning is called supervised learning. Right? How does the entrepreneur figure out the function F, relationship between temperature, pressure, etc., by collecting data and looking at some examples, and from there inferring it out. In practical terms, you're trying to find the best fit. Oh, it has a lot of my drawings have disappeared. Strange. Okay, you're trying to discover the best fit lines, the best fit curve to the going through the actual data. So but the problem again comes, machines are extraordinarily good at memorizing, just like kids. So when you don't want to learn, what will you do? You'll just go memorize it, isn't it? It's like your important questions for the exam. So what you do to prevent that, whenever you get data, right, to build a model. So suppose you get data. Let's take data. What you do is you take a part of the data, some part of it. Doesn't have to be half. It could be a little bit, it could be a lot, whatever. Some proportion of the data you take. And then the other proportion of the data, this part of the data, you hide it under the pillow, hide. Then you go to the model and you say that the only data you have access to is this data. It's called the training data. So this is the data you show the model to learn from. Are we together? But after the model has learned from this data, how do you know that it has not memorized? The technical word for memorization here would be overfitting, right? We'll come to that in a subsequent day, but today let's keep it just to high ideas. How do you know that it has not? Because just like the parent who took the child to see a duck, to identify a duck or a cow she had not seen, in the same way, this data that you hid under the pillow is a perfect way for you to validate whether learning has actually taken place. You would ask it to make predictions on this data, isn't it? To see whether it can identify the cow, she can identify the cow or duck, or in this case, the machine can identify. And that is why it is often called the test data or validation data. You validate the learning. Are we making sense, guys? Right. So that is supervised learning. You always do that. You split the data, you hide some under the pillow, call it test data, validation data, and you let the machine learn only from a subset of the data. So we learned about classification. These algorithms are called classifiers. So how many regressors and how many classifiers are there? Can you guess? How many types of regressors and classifiers there are? Algorithms. So many that we can't count. So many variants and types there are. So the field of machine learning is rich, and over the years, people have created lots of very, very creative, like amazingly insightful math they have used to create lots of classifiers and regressors. But again, we are going to give a whole day to classifier, one whole day to regressor. So I don't want to go into detail. I can give you a sense of that, little bit of that through labs, or maybe how are we doing with respect to time? Oh, we are getting close to, there are 2 more to do. Okay, guys, how about this? The Jupyter notebooks, let's bring it up next time. Right? And if I get time, I could quickly, actually, let me give you a quick sense of because sometimes practice, let's look at data set 1. Suppose you look at this data, univariate 1. This is the data. We'll learn how to load it and do all of this code. All of this code is very simple. We are using pandas. And scikit-learn, by the way, the libraries that are there. Tomorrow, I'll help you set it up on your laptop. I'll make you comfortable with this code. But today, we'll stick with big ideas. Guys, look at it. Suppose your data is like this. You did a plot of the data. What is your urge? What is the relationship? What is the function that you feel like guessing? Linear, a straight line, isn't it? It practically begs for a straight line relationship. We will do that tomorrow. We will create a straight line function, and we will learn basic things like so-called residual. One of the things that people often miss is something called residual analysis, which helps tell whether your model is right or wrong. I mean, is way off. No model is right, but whether your model is just barking up the wrong tree, right, is on the wrong track. So, by the way, those of you who have some background in machine learning, how many of you are used to doing residual analysis every time you do regression? So we'll do that. So as you can see, this data begs for a straight line fit, isn't it? You could, in the same way, look at another data. What is the data like? Suppose you get a data like this. Would you fit a straight line through it? No. Your hypothesis has to be different. You have to start with a different function. So if you build a straight line model, it will be foolish. So this is your model, straight line, and the data is completely different. So you can do things like polynomial regression. How about this model? Does this look better? Right? So how do you do that, et cetera, et cetera? We'll learn a little bit about it. And sometimes you get our data that I deliberately cooked up. But what if your data looks like this? Right? And you ask, well, what do I fit through this? And you can think about it. And after a little while, I won't go through it. We will do this lab. Tomorrow, let us say that you fit your data like this. Does it look reasonably good? At least a workable model, right? Or what people call your version 1. Yeah. So, well, these days it's fashionable that version 1, you call this version 1 and release it. Right, in the industry. You would call this version 2 perhaps. But you can do better and you can go on improving upon it. But we'll learn about all of that tomorrow, right? But I hope you're getting a sense of regression. I'm showing it to you only in one-dimensional data, but it's true. We will deal with it with a real situation, predicting. Oh, okay, here's one. So this is the moringa leaves, moringa. Most of you know what that is. Drumsticks, yes. So here the problem was to predict the relationship between the leaflet count and the petiole, the size of it. And when you scatter plot it, you notice that the relationship is very interesting. And if you try to build a linear model, it doesn't quite work. You try a different model, which seems to be a little bit better. How do you come to such models and so on and so forth? We'll learn about all of this. By the way, this was a real experiment we gave to one of the students who later on became our teaching assistant with us, Kyle. She will be there helping you guys forward. So when you do, typically when I do the machine learning course, which I'm not offering at this moment, we're going at a very fast pace, but when you do the AI course, the comprehensive intro to AI, when you do the formal courses, the 4-month-long courses, one of the things we emphasize is to gather original data. So we pull out our microscope and our vernier and our calipers, right? And we let you actually measure things and create your original data, because that is where science begins, by first taking measurements and then building AI models. So you have an appreciation of the entire journey. So it isn't that, oh, I wrote 10 lines of Python code. Look, I'm an AI expert. You go through the whole journey in that process. So this is very interesting. You learn, well, most of the topics are too advanced to teach in such a short duration, but maybe I'll talk about the California data set. California housing, if we have the analysis here. All right, so that was the second class. The third class of algorithms is called finding clusters in data. Okay? So what are clusters? We all know what clusters are. You guys today are a cluster of people in this room, but if you look outside, it's all empty. The parking lot is empty, the neighborhood is empty, and all of you are not uniformly scattered. You happen to be in this classroom as one cluster, isn't it? So when you see data as clusters, so let me just open one of them. One of the, so we like to create funny data sets. So let me show you one of the data sets that we created. Just to show you clustering. Oh no, let me take a real data set. Most of you have been to the Yellowstone National Park. So you know about the Old Faithful geyser. So the eruption time. So you know that if a geyser has erupted, how long it erupted, the longer it erupts for, the more it has lost steam, the energy, right? So it takes time to build up pressure underground. And so the wait time increases. You know that, right? So this is the eruption scatter plot. Just looking at this, if I were to ask you, is the data uniformly spread out? Or you see two clusters, eh? And that is the point, guys. Human eye sees it immediately. In fact, for two-dimensional data, you can literally take a pencil and draw the clusters. But in higher dimensions, we are not able to do it. We live in the world of very, very high dimension spaces where our basic intuition, our vision doesn't quite work. So now comes a different question. And then there is a data that I generated for this, just for fun. Let's look at this data. I call it the smiley data set. Can you guess why? Because it looks like this. Right? And do you see clusters here, guys? Right? They are clusters, right? But to confuse it, there are also points that don't belong to clusters. Do you see the pimples on the face? There's little dots all over the place. They actually don't belong to the cluster. They're outliers, isn't it? Away from the clusters. So anyway, we'll have fun with it in one of the sessions. And we'll discover actually this smiley data set is the reason I created it is because it is actually one of the most challenging data sets to cluster. It's not that easy. For reasons that you will learn. Well, let's keep that for another evening. Yeah. But basically, it is not that, though it looks straightforward, most of the algorithms actually fail miserably on it. For example, k-means cluster is a disaster, the most commonly used algorithm. And we'll learn a little bit about it on that day. So clustering is finding clusters in data. Are we together? Now, you remember that when you find clusters, you're not predicting anything, are you? You're recognizing a pattern in the data. But is pattern recognition machine learning? This question is worth asking. Is there any form of learning by recognizing patterns in data? So I'll sort of motivate it with a point. Suppose you are in San Francisco, downtown, and you feel totally lost. Imagine that the world doesn't have your Google Maps and all the maps in front of you, right? So what will you do? You have to get a sense of the place. You go up a little bit, you look, oh, okay, if I keep going like this, if I keep going, for example, east-west, right? And you're in the middle of the market street or something, there are more and more concrete buildings, isn't it? You might start going north-south, and you might see that, well, more concrete buildings are near the water than otherwise, but things like that. It takes a lot of time. You'll be lost for quite some time, figuring out what exactly does San Francisco look like. But suppose you're in a hot air balloon or flying over San Francisco, more like it. What happens? You look down, and in one glance, what do you see? You see the whole structure. You see the downtown, the commercial district, right? You see the Golden Gate Park, the green thing in between. You see, after that, the residential areas that pop up. In one glance, you have discovered the structure, the whole pattern or the layout of San Francisco. And so next time I drop you again on Market Street, and I say, go to the Golden Gate Park, you would know exactly which direction to go, isn't it? You may not know the names of the streets, or you don't need to. You have done. So have you learned something by recognizing patterns? You have, right? And therefore, pattern recognition too is machine learning. Right? So that is, and this form of pattern recognition is called clustering. There is another form, that is dimensionality reduction, but we'll come to that later. Let me ask this question. Clusters. If I get data, how do I know that they are clusters? Do I always know that they are clusters? So suppose I ask you this question, just in the abstract. Suppose I give you 1,000,000 data sets of all sorts of varieties. One is biological, one is about finance, one is physics, one is space, whatnot, like chemistry, sociology, psychology, and so on and so forth. Every imaginable kind of data. Huge diversity of data sets, 1,000,000 of those. Let's say that you went to Kaggle and you found that 1,000,000 data sets have been uploaded. In how many of those data sets would you actually find clusters, or you know that clusters exist? Give me a proportion. 4%, 3%, 5%. What percentage of those data sets are likely to have clusters?
Has to be low since you're asking the question, but I don't know how low.
Can you define what a cluster is?
Oh, look at this. The eye is a cluster. Cluster is where the points are. The points within a cluster are much nearer to each other than points outside the cluster. That's the definition of a cluster. It's a distance measure that tells it's a cluster. What proportion of this millions of this wide diversity of data sets would actually have clusters in them?
65%.
55%. 65%. Oh, very optimistic. You disagree.
Less than 10.
Less than 10.
All of them.
All of them.
30%.
95%.
Okay. So guys, I'll give you a counter examples and then let's see if your guesses change. Suppose I gave you on a beach the location of all the, like suppose I gave this sand lying there. It's all level. I gave you the XY coordinates of every grain of sand. Do you think there are clusters there?
Yeah.
No,
Yeah.
there are no.
No.
If I gave you, it's uniform sand spread out uniformly. There are no clusters. So obviously, 100% of the data sets cannot have clusters. Water, I gave you water, and I gave you the XY coordinates of, let's say there's a lake, and in one section of the lake, I gave you the XYZ coordinate of every molecule of water. Do you think there are clusters there? No, it's uniform. Right? So it isn't 100%, but let's go to the other extreme. Are there never clusters in the data? Well, you're staring at one, but are there never clusters in data? That too is not true. Right? You notice that everywhere around you are clusters of some form or the other. Clouds are cluster of water vapor. Forests are clusters of trees. And if you walk through the forest, you'll often find clusters of specific species of trees. Right? Clusters are quite prevalent. So the answer cannot be zero. The answer has to be somewhere in between.
But
And yeah, go ahead.
Asif, actually, it really depends on the granularity of the lowest substance that you're viewing, right? You're telling like like the sand particle or the water molecule. But if you think, okay, water bodies itself, water bodies near the river kind of things, there could be a lot of
Yes.
clusters in that way. But the way,
Yes.
like how granular you're going to go, like the more you go deep, you'll see less cluster. But if you go above, like trees are like you were mentioning about trees. Again, if you go much granular wise for a particular tree, then we may not find the cluster within the tree, right?
That's a very good point. Who am I listening to?
Wagish.
Vagish, actually, you made a profound point. Very, very true. And hold that thought and I'll mention to you. First, it is correct what you just said. The definition of cluster is predicated on your granularity, right? For example, in a water, I just said there are no clusters, all the molecules coordinates are spread out. But actually, the atom itself is a cluster, right? You take an iron atom, all the nucleons, the neutrons and protons, they're clustered in a tiny little zone and electrons buzzing around, right? So what is a cluster or is not a cluster is also a matter of resolution or granularity. But now let us ask this question. When do we see clusters? How often do we see clusters? The answer to that is quite interesting. And it's not an answer that you can anticipate, actually, unless you have training in chaos theory and nonlinear dynamics. The statement is this: wherever you have nonlinearity, invariably you'll see clusters. And how often do we have nonlinear forces at work in nature? Almost always. So most data sets, your presumption should be that it will have clusters. The question is, how well are the clusters formed? Right? Sometimes there are not. I gave you counterexamples, situations where there are no clusters. But your basic presumption should be there will be clusters unless proven otherwise. Now, here's the statement. What in this world is this chaos theory and nonlinear dynamics? They sound like fancy words, isn't it? I'll make it very real for you. See, have you noticed that when people send you, well, I'm an old-fashioned guy, so I'll just use the word letters coming to your mailbox, translate it to emails coming to your inbox, or messages coming to your WhatsApp and iMessage and Discord and all of those things together. If you observe, does it ever look as though some days everybody seems to remember you? You're getting messages from lots of people. And then, for no rhyme or reason, it seems that nobody is paying attention to you. You're not getting many messages. How many of you have observed this? Right? That the messages don't come at a uniform pace. They are bunched, right? Or in time, they're clustered. Have you noticed that? And the reason for that has to do with the fact that, anyway, I'll give you the reason later. Another observation. If you stand over a flyover, over a bridge, the road that is often there on top of a highway, and you look at the traffic going under the highway, it's fascinating sometimes, mesmerizing to see the traffic flow underneath when you're sitting on top of a highway. When you see that, actually, by the way, one of the places that I love photographing is on the Bay Bridge. Right? If you're on the Treasure Island and you're looking towards the part of the bridge that connects to San Francisco. So, you come out of a tunnel and you go towards San Francisco. Not many of people realize that what looks like wild, trees or rocks here, there's actually a little path there. And some of the best photographs that you can take is by going there with your camera late at night, putting it on a tripod and taking a long exposure shot. You'll see, you'll get beautiful shots of the Golden Gate. Of the Bay Bridge. And that's what the iconic pictures of the Bay Bridge have all been taken from there. So anyway, so suppose you're sitting there and you're seeing the traffic flow by. Even when there is no congestion, imagine there's no congestion, traffic is flowing on the highway. Do you find the cars all equally spaced? Or what do you see? They come in waves. One bunch of cars will come, another bunch of cars will come. Do you see that, guys? And then for no rhyme or reason, it seems that there's space between those bunches as they flow through, right? That is clustering. You see that, right? No rhyme or reason with clusters. The reason's actually deep. It has to do with chaos theory. It basically says that whenever there are nonlinear forces at work, like in this case, and there are multiple forces at work, invariably, you will have clusters, right? It goes a little bit deeper than that. The reason that the universe is the way it is because the universe is a chaotic system. Right? It's a nonlinear system. So when you look up at the sky, do you see all the stars equally spaced, or do you see them clustered in galaxies? Clustered in galaxies, isn't it? So clusters are everywhere. You're ever in doubt, just lie down and look up at the night sky. You see clusters, isn't it? So the process we'll give one day to finding clusters. It's a form of machine learning. It has tremendous application. So let me give a practical application for it. See, guys, let's say that news is happening. You are a news aggregator. So I'm giving you a little bit of a background on how things like Google News came about. Suppose you're observing all these news sources have gone digital. So they have web pages. All around the world, something or the other is happening. Human beings are a gregarious species. We talk, right? So a bridge develops a crack, we talk. It shows up in a local newspaper, isn't it? So suppose you want to be a news aggregator and find the news, like Google News, which is a news aggregator. What could you do? You could be listening to all the news sources. And Google is, of course, it is Spider. It's looking into all the news items coming from everywhere. Now, pay attention to what I'm going to argue. All of these news sources, whenever you create a newspaper, what do you want to show? The big ticket items. So let us say that somewhere something happened. For example, these days news is so frivolous, I can't even think what should be the news. Let's take somebody makes a major discovery. Oh yeah, these days, of course, we don't have to. The biggest news is a deep sea carbon gets released, right? So what will happen? There'll be chatter. Different news medias, different sources will start talking about it. You don't have to know what they are. You just pick up those items and in a text space, you cluster them by what they're talking about. What will you see? From all the different news sources that are talking, you just aggregate all the text. Will you naturally see a big cluster forming around this discovery called deep sea carbon or something? Yes. Right? Somewhere else, some politician is doing something very politicky, whatever it is. Maybe he resigns, maybe he's elected to power, whatever it is, right? Or passes a law, and that has huge impact. So there will be some chatter about that, and that will be a naturally emerging cluster of text. So what does a news aggregator have to do? Keep an eye on the emerging text, do a clustering in the text space, pick the biggest cluster, and whatever news item is at the center of that cluster, whichever news source, just make that the headline, isn't it? Are you seeing it, guys?
Yes.
Which is why when you go to Google News and things like that, have you noticed that sometimes the sources they put is very impartial? It isn't that, they'll always put some big newspaper as the core source. So observe, whatever it is, how many of you, look at the front page, how many of you knew a news source called WBAL TV Baltimore? Nevertheless, it is on the cover at this particular moment, isn't it? How? Because it was at the center of that cluster. If Google had used the clustering algorithm, and from my understanding, the initial version, that is the approach they took. So do you see how these ideas that look abstract have tremendous practical implications? Right? And by the way, again, being a machine learning exercise, somewhere or the other, Google used to claim that they produce a new newspaper, new version of Google News every 8 minutes. Just think of the scale of it. Right? All you have to do is recluster the data every 8 minutes, isn't it? Well, there's more than that. It isn't just clustering, there's topic detection. There are many, many AI algorithms that come at play, but I'm sort of oversimplifying it and saying you could do it like this. Am I making sense, guys, about clustering? Right? Very basic thing. You get astronomical data. Galaxies are the clusters, right? Machine learning has revolutionized astronomy. Now, the final form, I know you guys are getting tired. I'll just talk about the last core pillar of machine learning that I haven't talked about. It is dimensionality reduction. And I'll keep it very intuitive. Suppose you get data in very high dimension space, or let's make it very practical. You are trying to find whether somebody will have diabetes or not, or has a likelihood of getting diabetes. So you may be, one of the variables may be, one of the dimensions may be the weight, another dimension can be the age, another dimension can be the height. So you can find the, what is it called, BMI or something. Another dimension could be the fasting sugar or something like that, right, on a given day. So you can have many dimensions. Somewhere in there is also the color of shoes the person wears most regularly. Because you might think, somebody might think in a hypothetical world that matters, or the color of the shirt, right? There may be many variables. Only later, through experimentation, through modeling, do you realize what matters and what doesn't matter, right? You figure out how much vegetables the person eats, how much of food, and so on and so forth, nutritional data. It's all there, right? Irrelevant things, relevant things, etc. They're all there. Now, suppose you could, off the bat, tell that in this data, because you built some preliminary models, right, you realized that the color of the shirt and the color of the shoe don't matter. It's unfortunate. I was hoping it mattered, but easy cure for diabetes, isn't it? But it turns out it doesn't matter. And you take those out. What have you done? You have reduced the dimensionality of the data right away. Simply reduced it. That kind of reduction, there are techniques like lasso regression, etc., that bring it about very effectively, that helps you sieve through your predictors, through your features, through your input variables, to tell which ones matter really and which ones don't matter. And that brings up a bigger question: to what degree it matters. That is the whole question of feature importance, but let's not go there. But let's say that some things don't matter, or they matter so little you can just throw them out. Now you have reduced the dimensionality of the data. Isn't it, guys? Now, in the same strain, you don't get life so simply. In a more real sense, today, people have often looked at gene expressions and asked which genes are causing a disease. Right? Sometimes you're lucky. You find that for very rare, certain rare diseases, most of the genes don't matter. Only one gene matters, or two genes matter, right? So when only one gene matters, you're really, really lucky. You have identified it. You can do something about it. Yeah. We live in the world of CRISPR and so forth. You can do something. So you have reduced the dimensionality of the problem down to one. Yeah. Human body has a lot of genes. A chromosome has a lot of genes, right? DNA. So now that is rare actually. Most diseases are polygenetic. In other words, they are the conspiracy of many genes coming together and doing some mischief, right? Getting into not a good state or whatever it is, the biologically or medically appropriate terms, the expressions go off collectively, right? The gene expressions. So you do have those diseases, and then there's epigenetics and so forth. It's a very complicated subject, but I'm oversimplifying it. Sometimes, let's get back to the problem of diabetes. So suppose you build a very complicated model which has to do with cabbages, how much cabbages you eat and how much you walk and what your weight is and what your age is and so forth. And you go to the doctor and the doctor says, okay, I'll give you a regime. Make sure you wake up in the morning, and the moment you wake up, you drink hot water with lemon in it. And after that, have exactly this amount of cabbage and that amount of that, and you be on the treadmill for 3 minutes, and you do this and you do that. And after a little while, the patient is totally lost and beginning to lose confidence on whether she can follow the regime, right? On the other hand, you go to another doctor, and that doctor says, my dear friend, do two things. Greatly increase your exercise, really increase your exercise, and moderate down your food, especially at night or something like that. Two things. Now, which of the two advice is likely to be followed?
Second.
The second one. It makes sense. What has the physician done? concluded that the underlying forces really at work it's a metabolic disease, and some of the drivers are the amount of exercise the body is getting and the overconsumption of food. We all love food, we love sugars, right? It actually goes back to prehistory. Apparently, somebody told me, I don't know if those theories are still true, that our species interbred with another species, and through all of that came the real gene for love for sugar or something like that. God knows what it is. I find this theory is very far-fetched, but who knows? I'm not a biologist. So how did the second advice come through? What you did is from all of the variables, you synthesize a new variable, right? Something like exercise level or food calorie consumption or age or something. You took the original raw variables and you synthesized something out of it. Like a classic example is, how do you get BMI? A BMI is synthesis of your weight and your height, isn't it? It's a synthetic variable. So what if you could take the data and synthesize a lesser number of variables out of it and represent the data with lesser number of variables? What have you done? You have reduced the dimensionality of the data. Now, when you do that, sometimes you lose a bit of information. You say that, some things may matter, but not to such an extent. Right? You throw that away. But why would you be willing to sacrifice some of the signal just to reduce the dimensionality of the data? You remove the noise, but also practical reasons. Like in the case of this two physicians giving advice, the patient is going to follow a simpler advice than a complicated advice. In other words, you show the patient a world of two dimensions, just two axes to work on. The patient is actually going to do something about it. More specifically, I'll tie it back to vision, to visualization. If I could bring the data down to 2 or 3 dimensions, what do I have access to? The most powerful learning system in the world, namely the human eye. You could find and discover all sorts of things in the data immediately, isn't it? If I could bring it down to 2, 3 dimensions. Beyond that, you start getting lost. Right? So there is a lot of value in doing what is called dimensionality reduction. Now, it's a big field, and I've oversimplified it. There are lovely tools, starting with PCA, Principal Component Analysis, which was discovered in the 40s, I believe, 30s or 1930s, 1940s, to the state-of-the-art ones, which we will do if you do the fundamentals of AI course. You will learn about things like autoencoders and so forth. And you will also learn about techniques like UMAP and TSNE and autoencoders and many things that do represent data in certain latent embedding spaces of lower dimensions. Right? In fact, the search for the best low dimension or meaningful dimension of our data, some people consider it to be the heart of machine learning. So that is the field, guys. I know that it's going to be 10 o'clock. I would like to give the last 10 minutes to question and answer. But I gave you, today we didn't do much lab or practical. Next time, please bring your laptops so we can do a little bit of hands-on also, which will be tomorrow. Next session is tomorrow. So I hope this gave you a reasonable sense of what machine learning is and what its core components are, core areas are. So I'll take questions now.
On our laptops, what kind of environment do we need to set?
Just make sure, see, if it is a Mac or a Linux, you're in good shape. If you are on Windows, make sure that you install the Windows subsystem for Linux version 2. In other words, make sure it has Ubuntu on it. Right? Either directly through the WSL2 or as a VM, doesn't matter. Because see, the AI community, for all practical purposes, is very, very Linux heavy. Yeah. Mac is close because it has a Unix root, and Windows is a little too far. Yeah, thank you.
Do you recommend all of us to install VS Code and Panda, or should we go to UE?
No, just UV. So maybe I could give a demo of UV, but no, we don't have time. But-
Put on the Discord.
Oh, yes, there is a video, guys. Could I ask you guys to follow through one video? It was a session that you guys missed. If you go here, so we have a YouTube channel. I invite you to subscribe to it. As you notice, there are close to 600 videos there. If you go to the videos, yeah, do you see this video called Setting Up the AI Development Environment?
Just always do develop.
So this is a video. If you guys can, are you guys, by the way, just some housekeeping. Did you guys all join the Discord?
Yes.
So on the Discord, let's post it to Discord.
Question, Asit,
Yeah.
have you converted all the code base to UV?
I'm in the process of doing it, but as we go along, this one, the code that I'll release tomorrow, will be using UV. UV is a new way, guys. Huh? Many of you, almost all of you know Python, of course, but you might not know UV. And so it's a new way of doing things. General discussions. So there is this video, guys. Huh? I'll just invite you to watch it and follow along and finish the setup before you come next time. Are we together? And if you are here, I can take you through a very quick setup step because it's literally 2 minutes. Would you like to see it? Yeah.
So actually, the ensure that as
Oh, yes. I've released it actually.
So what we found was some of us have Mac based on Intel.
Mhm.
So the dependency on SV boot, the FitPy, right? It depends on Torch 2.5.1.
Mhm.
So the Mac Intel does not have that version.
Oh.
So I was just debating that. So either we need to change the version dependency in your bootcamp to 2.1.1, which supports, for which the support is there. So what I'm going to say is if somebody has Mac based on Apple, that ensure it works because it downloads that version of the Torch.
Yes.
Some of us, like I have Intel based.
So you need a hack.
So the thing is, the insured script depends on your
my projects, yes.
my project, right? So you might have to change the Git. I mean, right? There you have to change. Otherwise, it goes there and downloads. So I was trying to see if I can make the changes locally so that my dependency points. When I have to create a local dependency, actually. Either you have to change there or
no, you don't do that. Don't use that. What you do is you run the ensure config, it will fail. But then ignore that. We will hand edit the Pi project and I'll tell you how to hand it. That is it. And then all will be fine. Now, if you want to just quickly fix it right now, go to your Pi project and where it says dependency SV Learn Bootcamp, change it to SV Learn Core. Because for this, like for a simple machine learning course like today, you don't need PyTorch and all that. So if you make it core, it reduces it will be fine. You can check it right now. Just change it to core and then just do a UV sync upgrade, UV sync and UV build. It will immediately work. Yeah, just change it to SV core. Yeah. So if you guys have the time, I'd like to show you how to do it. Let me bring it up, guys. So I will open a new shell. So guys, look at this. This is a little shell on Mac. It could be a shell on Linux or on, if it is Windows, you can do that. So let's create a project, UV innate. Let's give it a name of a project. What would we like to call it? Here, bootcamp.
The data science bootcamp, DS.
DS bootcamp. The DS bootcamp. Is that okay?
Yeah.
Right? And you say Python is equal to 3.12. It's good. It's one version behind. That should be good. So you look at this. I'm giving only one command, and you'll have instructions for all of this. It got created. I will go to DS bootcamp, and I will do UV sync, and everything got created. If I do, my whole project got created. Now let's add a dependency that you'll find useful if you are with me. You can say UV, add a dependency on SV Learn. Let's say core. Those of you who want to do neural networks, should say boot camp for the upcoming boot. By the way, how many of you have registered for the boot camp of one of the courses in Fed? You have. Nice. You guys have. So if you haven't, it's okay. Then just do SE code. It added a dependency, and that is it. Your complete environment is set, your project is set up to work on, and you can do more fancy things. But at this particular moment, 3 commands, you're done. So, for example, if I want to build your project, I can say UV build, and look at this. You are ready to publish it. Even your wheel file is created. Do you see how easy it is to create the environment in Python? Now, here's the thing with UV. You don't even have to install Python. Just install UV. It will install, when you say the version of Python, it will locally install the version of Python that is needed. Right? So if you have been using Anaconda, Municonda, Pip, Pipex, Poetry, forget about all of this.
How do we install UV?
Oh, how do we install UV? Well, by watching my video. No, I'm kidding. No. There's a simpler way. Just let's look up the UV documentation. UV install. See, here's the thing. This is one line. To install UV, you just need one line command. Where is it? Yeah, this is it. Do you see this one line command? That is it. Just give this curl command, assuming you have curl, and this one line will install UV on your machine. After that, I'll just recap. You realize that to get a fully working project, I just did 3 commands: UV init, UV sync, and then I build the project. You go write your code and then build your project. And then at that moment, you load it into your favorite IDE, your Cursor or VS Code or PyCharm or whatever is your favorite IDE. I would strongly advise you to use an IDE. I know that many of us are VI diehards. The problem is we live in the world of AI. AI writes 70 to 80% of the code now for us. So you don't want to skip on that opportunity.
So, so Asif, just to understand, so is the suggestion to move away from Anaconda and use more?
Oh, completely. Forget about it. Anaconda is, first of all, there's a licensing issue. You can use it for small projects, but the moment if you're in a big company, you shouldn't be using it. You're not allowed to.
Okay. So UV is the choice.
UV. So the open source sort of a workaround Anaconda was Miniconda, but why bother? UV is the new thing. Watch my video. See, guys, why UV? Watch my video. You'll see it.
Okay. Thanks.
So I've put that video link in Discord. Watch it. UV is all the open, you can see that most of the open source projects have started migrating to UV. All right, guys, any questions? Anybody has a question before I close? Thank you for your time. Let's see. We'll know whether this session was useful or not based on whether a single soul shows up tomorrow.